welcome to the tutorial, okay, about an isomorphism. Okay, I'm going to write the question here. So, for the map, split it into two. For the map, f defined from P1, okay, polynomial of degree 1 to R2, given by ax plus b. Okay, we associate a minus b, this vector. So the question is as follows: show that f is an isomorphism. Is an isomorphism. Okay. So if you remember from our previous video, we have seen the how do we show that a map is an isomorphism. We have to show two main things, or four in total. The two main things, okay? The first one is a correspondence. We need to show that f is a correspondence, and by correspondence we mean show that f is 1 to 1 and f is 1 to. The second main thing we need to show is we need to prove is that f preserves structure, and by preserves structure we mean that f preserves vectors addition and scalar multiplication. Okay, so this is going to be how we are going to do the question. Okay, first of all, we need, so I'm going to write solution here. So this is going to be the solution. We need to prove that number one, A is correspondence. So we have a correspondence. Okay. One, we need to prove that f is a correspondence. Let me write it just for those who haven't watched the previous video yet. Okay, let me give you the full sentence of solution. Okay, to show that f is an isomorphism, we need to show that f is a correspondence and f preserves structure. So we need to prove these two things, okay? Correspondence and f preserves structure. So here, let me label it. Number one, we need to prove that f is a correspondence. F is a correspondence. Okay, by correspondence, if you remember the previous video, we need to prove two things. F is 1 to 1, okay? And to prove that f is 1 to 1, we need to assume two vectors from the codomain, the domain space, and say that, equate the images of those two vectors from the domain space, and then derive that, those two elements are the same, okay? So let me keep the colors the same so that people can follow the logic. So we need to prove that f is 1 to 1. Okay. So how do we prove that F is 1 to 1? We have said it already. We are going to assume, okay, V1 and V2, true element, and V2 from P1. So, okay, that's such that, okay, that means V1 is going to be equal to A1 x plus B1, and V2 equals to A2 x plus B2. So true element from P1, such that F of V1 equals to F of V2. Okay, so we'll assume that such that F of, yeah, let me write it here, F of V1 equals to F of V2. So, and then do some manipulations. Okay. Even if you want, let me change colors here, because this, you know, this proof looks easy, but you have to pay attention. So we have to assume that F of V1 equals to F of V2. Okay, we will assume that, and then do some manipulations so that at the end we can have V1 equals to V2. That's what we need to prove. Okay, so we take two vectors from P1 and we assume that F of V1 equals to F of V2, and I have already explained that in the previous video. Okay, that F of V1, the images are the same in the codomain spaces are the same. To prove that if the images are the same, that means the elements in the domain are also the same. V1 equals to V2. Okay. So now how are we going to prove that? If F of V1 equals to F of, we say that V1 is A1 x1, so we have A1 x, sorry, plus B1, that's V1, equals to F of A2 x plus B2. Okay, so does what does the map do to an element from P1? It says it turned that element into a two-dimensional vector. So we have A1 minus B1, B1, okay, equals to A2 minus B2, B2. So how do we prove that the two vectors are the same, or when do we say that the two vectors are the same? And yeah, we have seen that in one of my previous video, linear systems, the first main chapter. We have seen that for two vectors to be the same, they must have the same component. Okay, so this vector is the same as that vector. That vector means that A minus B, A1 minus B1 equals to A2 minus B2, and B1 equals to B2, B2 exactly. So if B1 equals to B2, that means here as well A1 equals to A2, if you see. So that means what? Here we have, let's look at our vector again, A1 minus B1, B1. We say that A1 equals to A2. That means instead of A2 here, instead of A2, I can just write, let me see, here, if we say that, the vector is the same, so sorry. So here, A1 equals to A2, B1 equals to B2. That means my vector, V1, okay, which is equal to A1 x plus B1, okay, can be written as, instead of A1 is A2, because we said that A1 equals to A2, can be written as A2 x plus B2. Okay, A1 is equal to A2, B1 equals to B2. So what does it mean? It means that V1 equals to V2. Therefore, okay, if we assume that f of v1 equals to f of 2, okay, we can prove that v1, that will lead to v1 equals to v2. Okay, so that means f is 1 to 1. Okay, so next, in the how to, okay, we need to prove that f is onto. Let me go to next page. So here we need to prove that f is onto. And how do we prove that f is onto? It says here we will assume W from the codomain space and find a V in the domain space that maps to the W. Okay, so we have let here we will call W is from the codomain space, which is R2. Okay, and so I'm going to call that R2. Okay, I'm going to write that W equals to Mn, so not M over N, just N, the vector Mn, the two-dimensional vector Mn. Okay, so what we have to do, what we are asked is to find V in P1 that will map to this W. If you remember, F maps ax plus b. Okay, f maps ax plus b to a minus b. So if W is an element of R2, that means W can be written as the difference of the two components, and then the second component is going to be. So this means M equals to A minus B and N equals to B. That means we have, okay, yeah, that means here A equals to M. Okay, so let me rewrite it this way just to keep the logic the same. Okay, so we have that means A minus B equals to M and B equals to N. Okay, we want to find A and B such that the vector M and N will map that ax plus b to the vector that we I know is a lot of talk. Let me work it out here. That means A is going to be M equal to M plus B, which is M plus N. That's our A. Okay, and B is this. Okay, so okay, let me write it. A equals to M plus N. So that means if I have a vector, okay, for every vector W M, which is Mn, okay, I can find there exists a vector V, small v, which is going to be equal to, it's not a two-dimensional vector. This is going to be a small v, okay, the v is in P1, A, M plus N, X plus N, okay. So if I have a vector W, I can find V in the domain space such that f of V equals to our W. Okay, that means f of V equals to our M N. Okay, so this is what we have to prove is here. So if we are given a vector W, we need to find So if we are given a vector W, okay, we need to find a vector V that will map such that f of V equals to W. Is that okay? So this is the main thing. We assume this, okay? We assume this and we prove that we can find an a V, okay? So that is what we mean by f is onto. Next is to prove that from the how to, f preserves structure. And let me go to next page. Is 2. We need to prove that f preserves structure. And by f preserves structure, we mean f preserves vectors addition, okay? And how do we prove that? From the how to, we will assume two vectors from P1, in our case P1, okay, from the domain space, and then we will prove that f of V1 plus V2 equals to f of V1 plus f of V2, okay? So we assume V1 and V2 from P1, our domain space. That means we have V1 equals to A1x plus B1 and V2 equals to A2x plus B2. And now we need to prove that if f of V1, or we need to prove, yeah, we need to show if that's true, f of V1 plus V2 will, okay, if it will give us, we will do some manipulations and found that, and find, we need to do some manipulations. We need to do some manipulations and find at the end that f of V1, okay, equals to f of V2. Do you see how we prove that? Okay, it seems easy, but you just have to be careful about what you are asked to find, okay, what you are proving, what you are doing. So we will assume f of V1 plus V2, and let's see if at the end, yes, it will give us f of V1 plus f of V2. For the moment, we don't know yet, okay? So that is f of V1 plus V2. V1 is A1x plus B1, okay, then plus V2, which is A2x plus B2. How do we add the polynomials together? We add the coefficient of the same terms together, okay? So this is going to be f of, okay, A1 plus A2 times x plus B1 plus B2. And our map says, what does our map say? F of, you know, ax plus b will give us what? Here, the map is here. It will give us a minus b, okay, the coefficient of the x term minus the constant, okay? So the coefficient of our x term is a1 plus a2 minus the coefficient of minus the constant. So we have minus b1 minus b2 over the constant term b1 plus b2. Okay, so we can, let me rub this off and maybe we'll go to next page. Here, what we can do is we can split this vector into two. Okay, my a1 minus b1, okay, plus a2 minus b2. You see, okay, and here we can have b1 plus b2. So now we can split the whole this big vector into two vectors. Okay, so we have a1 minus b1 plus a2 minus b2. Okay, so this is the same as what? F of v1 plus f of v2. See? So in conclusion, we can conclude, okay, that f of v1 plus v2 equals f of v1 plus f of v2. Okay. So here we have proved that f preserves vectors addition. The next step is to prove that f preserves scalar multiplication. Okay. So I will go to the next page. So here is, let me write small 2 here. I want to show that f preserves scalar multiplication. Okay. So let's have a look at how to again. So the first step is to prove correspondence. We have proved that f is 1 to 1, f is onto. We have also proved that f preserves vectors addition. Now we need to prove that f preserves scalar multiplication. So for all v in v1, okay, we want to prove that f of r being a scalar multiplied by v is equal to r times f of v. Okay. So let's go. So what we have to do is we have to assume v1, okay, in p2. So let's assume v1 so we have to assume v, let's just say v, an element of p2, the domain space. So that means v is equal to ax plus b. Okay, and then r, let's assume also r is scalar. Okay, so now let's write down f of r multiplied by v, scalar multiplication. This is equal to f of r times v. V is ax plus b. Okay, so this is f of r ax plus rb, and what is the action of r of f on that vector is, okay, we say that it takes the coefficient of the x minus the constant as the first component, and you use the constant as the second component. Okay, so here the coefficient of x is ra, so f take ra minus the constant here is rb, and then the second component is the constant rb. So that is the action of f on that vector. And we know how to multiply a constant, a vector, by a scalar. Okay, so what we have to do is we can take the r out. R, this is the same as r multiplied by a minus b. Okay. And what can we notice? We have our r there, we have our vector here, a minus b, and b is f of v. Okay, so this is r times f of v. You see, so f r dot v equals to r times f of v. So yes, this means f preserves scalar multiplication. Okay, so here I can just write a sentence here. This means that f preserves vectors addition. Okay, so this is the end of this tutorial, and I just want to give a quick summary. This is the question. So we have been given a map. Excuse me, we have been given a map, and so this is our map. It turns degree 1 polynomial into two-dimensional vector. Okay, so we are asked to find that f, to show that f is an isomorphism, and as we have seen in the lecture, to prove that a function or a map is an isomorphism, we need to prove two main things. We need to prove that f is a correspondence, and f is a correspondence, and f preserves structure. And by correspondence, we mean f is one-to-one. Okay, and so here is the how-to. Let me show you the how-to. So f is one-to-one, and f is onto. By preserves structure, we mean f is it preserves vectors addition, and it also preserves scalar multiplication. Okay, so basically this is what we have done in this lecture, tutorial. And I think there is a small, here I say v is an element of p2. No, we are working with p1. Sorry about that. Is degree 1 polynomial. So it's p1, not p2. Okay, so I'm going to stop this video here, and see you in the next video. We will continue with the lecture. Thank you.